Now that we have linear combinations in an arbitrary vector space, we can talk about spans in an arbitrary vector space. So just like in a Euclidean space, in an arbitrary vector space, the span of some subset is the set of all linear combinations of vectors coming from that subset S. So the span of S is just, right, you can choose any coefficients, any scalars, and any vectors from S and form a linear combination. And the set of all such linear combinations is the span. Okay, so as an example, let's look at polynomials. So remember, P sub 2, this is all polynomials of degree less than or equal to 2. We could ask, here's a polynomial. Let's call this P1. Sure, well, let's call it P. So here's a polynomial of degree less than or equal to 2. Is it in the span of these other two polynomials? So let's call these P sub 1 and P sub 2. All right, well, in general, right, it's kind of, if you think about Euclidean spaces, how do you check if a vector is in the span of two other vectors? You have to set up some sort of system of linear equations. Well, it turns out for an arbitrary vector space like this, it works out pretty much the same way. This is always going to come down to solving some collection of linear equations. We just have to be a little careful in how we set things up. So what we're asking is P a linear combination of P1 and P2, right? That's what we're asking. Or another way to say that is, are there scalars A1 and A2 so that P is A1 P1 plus A2 P2. Right? This is the question we're trying to answer. But just like if all of these P's were vectors, we could just write down what each one of these things is and see what sort of equation it gives us. So on the left, the polynomial P is x squared plus 17x minus 11. On the right, we have A1 times P1, which is x squared minus 3x plus 1, plus A2 times P2, and P2 is x squared plus x minus 2. Okay, and how to check if it's possible to choose A1 and A2 so that these things are equal? Well, I mean, how can you tell if polynomials are equal? One nice thing about polynomials is polynomials are equal exactly when their coefficients are equal. So what we can do is just rewrite the right-hand side, gathering up like terms. When we do that, we get A1 plus A2 times x squared plus, let's see, minus 3A1 plus A2 times x plus, and then for our constant term, we get A1 minus 2A2. Okay, we want to know, is it possible that this could be equal to x squared plus 17x minus 11? And since polynomials are equal exactly when their coefficients are equal, we can turn this question about polynomials into a question just about the coefficients. So the x squared coefficient on the left is 1, and on the right, it's A1 plus A2. On the left, the x coefficient is 17, and on the right, it's minus 3A1 plus A2. And then on the left, the constant coefficient is minus 11, and on the right, it's A1 minus 2A2. So now that we've done this work, you can see we've replaced this question about polynomials into this system of linear equations, and we're really good at solving systems of linear equations, right? In fact, we could rewrite this system of linear equations using a matrix. This is 1, 1, minus 3, 1, 1 minus 2 times A1, A2. We want to know, is there some solution where the right-hand side is 1, 17 minus 11? And to do this, you know, do what we always do. Augment the matrix on the left with the vector on the right, like this. and then we can row reduce. So you get to watch me row reduce one more time. So 1, 1, 1, and then add 3 times first row to the second row. We get 0, 4, 21, I guess. And then subtract the first row from the second row. We get 0, minus 3, minus 12. Is this? Okay. Now I'm hesitating because I thought I set this up so there's actually a solution, but maybe I screwed up. So let's see, we can do third row times minus a third, and we can do second row times 1 over 4. So 1, 1, 1, 0, 1, 21 over 4, 0, 1, minus, plus 1 over 4. Sorry, plus 4. Okay. All right, you can see that if we use this 1 here to zero out that entry here, we're going to get, this last row is going to be 0, 0, 1. Right? So it doesn't matter what's in the rest of this matrix. Since we have this last row is 0, 0, 1, this is corresponding to the equation 0 equals 1, which, there's no solution. So the original question, is this polynomial in the span of the other two? The answer is apparently no, unless I made some sort of arithmetic mistake here. So what we'll see this happen again and again as we work with general vector spaces. When we ask questions in general vector spaces that are similar to the sorts of questions that we used to ask for Euclidean vector spaces, we can always translate these questions into questions about matrices full of numbers and column vectors. Okay, so all of the computational tricks and ideas that we had for Euclidean vector spaces, we'll be able to carry all of that over to our work in general vector spaces.